Hi everyone, so today I'll be talking about electrophilic addition reaction. Similar to nucleophilic last week, electrophilic is just the opposite, so just means electron loving, and they involve usually alkenes, which we need to know for the IB. We all know that because of the double bond of alkenes that they are able to undergo addition reaction. This mechanism just kind of shows how this addition reaction works. Okay, so I'll be using ethane and hydrogen bromide to explain the mechanism. So what we know here is that in the double bond, we actually have a high electron density, and that it is in a pi bond. We have a pi bond here, which I'll draw like that. Oops. And we know for hydrogen bromide, it is actually a polar molecule because there is an electron negativity difference between the two of them. So hydrogen is slightly more positive and bromine is slightly more negative because the bromine is holding on to the electron in their bond a lot stronger than the hydrogen. So you can tell then, as the hydrogen bromide then reacts with the ethene, the positive hydrogen is attracted to this electron density. This makes the hydrogen bromide the electrophile because this is the one that's attracted to the high electron density of the carbon. So the red arrow is showing the direction of travel, and an important factor that's very necessary for this reaction to occur is that there need to be the electrophile, in this case the hydrogen bromide, needs to have the correct orientation to have a successful reaction. So we kind of need the hydrogen to be facing towards the high electron density. Okay, now we understand the reactants a bit more. I'll go over the mechanism. So first, as the hydrogen bromide, it'll go towards the electron density of the carbons because of the polar nature of the molecule. So then what happens is that because the hydrogen is slightly positive, the electrons in the carbon, in the double carbon bond, moves to the hydrogen. And then in turn, the the electrons in the hydrogen bromide bonds moves to the bromine. So because of this, what we end up getting is this. The double bond breaks, and we have a bromide ion. So what happens when the hydrogen is added to and breaks the double bond of the carbon? We end up getting a carbon cation. So as you can tell, this carbon has one less electron than it usually does. So because of this, it now has a positive charge. And what do we have with the bromide ion? A negative charge. So the two electrons in the bromide ion will then be attracted to the carbon cation. Then our final product will then be a bromoalkane. However, it is important to note that 50-50 chance that the bromine ion could be here instead. And we have another hydrogen here. And this is because, as we can remember, we have like a pi bond here. So the electron could either come from here or there. With the last example, we saw a reaction where there's a 50-50 chance of either isomers to be produced at the end. However, this is not always the case, especially when the alkenes have a different number of hydrogens on both sides. As I showed here in the red and yellow, there are two different pathways and two different isomers. This one is, we call it the 1 carbon cation pathway, because the carbon cation is attached to a carbon where there's only one other carbon attached to it. And then this one is called a 2 carbon cation, because the carbon cation is attached to a carbon that's attached to 2 other carbons. Okay, so Markovnikov's rule helps us to infer which of these two products are most likely to occur at the end of the reaction. And the rule states that the hydrogen is more likely to bond to the carbon cation with the most number of hydrogens attached to it. Oops. So knowing that, can you guess which one? Well, it would be the 2 carbon cation would be the most likely product to be produced at the end of this reaction. And the reason why is because this isomer is a lot more stable than the other isomer. And this is because since the carbon cation is attached to more alkyl groups, the alkyl groups being this one and this one, there are more sources of electrons to kind of stabilize the positive charge that we have here. So there are more electrons flowing to the carbon cation to stabilize this. However, with the first carbon cation, we only have one alkyl group to send in their electrons to stabilize the positive charge. So, very easy, Markovnikov's rule. There's just one final thing that I would like to add in addition reactions with alkenes. It doesn't always have to be like a hydrogen bromide or like a hydrogen chloride. There could be the other reactant could be something without the hydrogen, for example like an iodine chloride. And the way you can figure out which of the two elements will be the one attached to the carbon will be kind of the one acting as the hydrogen in the reaction. You look at the electronegativity in the data booklet. Since iodine is less electronegative than chlorine, this will be the one that's slightly positive and slightly negative. But regardless, the reaction and the mechanism will all be the same. So don't be afraid if you see a reactant that doesn't have a hydrogen in it. Just look at the data booklet. Okay, thank you for listening.